CLion, a cross-platform IDE for C and C++. Download now.
Thanks for the introduction, Jim, and thanks for having me, and thanks for coming to my talk, of course. So, Jim already told you the title, classes C++23 style, and there is a little caveat here. This is more like C++20-ish to C++26 style. So a lot of things came together on how to write data types, classes in modern C++. So a few preliminaries. So all the code samples that I will show you, they did compile with some compiler at some point. Everything is using namespace std implicitly for brevity, and all the code samples are shown in UTF-8 encoding, which you cannot tell on the slides. But I just wanted to mention this because it's now an officially supported source file encoding, which is right out of the gate, obviously the best C++23 feature there is. So before we're starting to go more into detail, like how we can write classes in modern C++23, let's first go back and ask ourselves, like, what actually is a class? What are we talking about here? And I'm sure you know some definition from object-oriented programming, but I went way back to the origin of object-oriented programming, which is Smalltalk, of course. And there's a book, although it's a paper actually, The Early History of Smalltalk by Alan Kay. And there's this wonderful quote where he says, when he was coming up with classes, he said that instead of dividing computer stuff into things each less strong than the whole, like data structures, procedures, and functions, each Smalltalk object is a recursion of the entire possibilities of the computer. Now, isn't that a wonderful definition? It's a recursion of the entire possibilities of the computer. And the way he was thinking about classes and objects was that he wanted to make programming both user-friendly for novices and also expert-friendly by representing real-world things in those things that he called objects. So objects for Alan Kay and for us as well, they typically have meaning or they have semantics. And we'll come back to some typical semantics that classes have. In this paper, there's another great quote that I wanted to share. There's nothing to do with my talk, but everything with the world. He was thinking about computing in a much bigger way. He was thinking about computing, and he was thinking about its potential to amplify human reach and bring new ways of thinking to a faltering civilization that desperately needed it. Now, this was the 60s, which wasn't as great as people now remember it. But I think this is a wonderful quote and should sometimes think about our work and if it also amplifies human reach, because maybe that's something we should aspire to. Okay, now back to basic C++. What is a class in more profane terms? The definition you probably know is that a class is a unit of data and code. So in C++, it means that it has constructors, it has these destructors, base classes, access control, template arguments, whatever. These are all the syntax of a class. But a class, as I've said, should also have some meaning. It should represent something in the world, at least in the mental world of your project. So what do classes typically represent? They might represent a simple value that you pass and copy around in your program. They might represent a container that stores data, a resource like a file or a data structure that's typically something that we have to clean up when we're done with it. Or it might be semantically a singleton, of which you can only ever have one in your entire program. When I write a new data type, when I write a class, I first think about the semantics of that class. What kind of thing is that? And it often fits in those 4 categories. And when I've decided that, I have already decided what lifecycle that thing should have. So the lifecycle here means, how do I have to implement the constructors and destructors? And which ones do I have to implement? And when I say which constructors do I have to implement, you are probably already thinking of this famous table So this is from a talk by Howard Hinand in 2014, so over 10 years ago, about move semantics. And it shows the rules which special member functions, so constructors and destructors, will be implicitly declared by the compiler or deleted depending on which constructors you declare. Now, this is very complicated, a very simple visualization of an in detail pretty complicated concept. I've occasionally consulted this table, but I will show you a much simpler way of implementing the correct lifetime of your objects. And that's by looking at what semantics this classes will have. So I've showed you 4 different semantical classes. The first one was simple value types, things you pass around. So the informal definition of a simple value type is it should behave just like an int. There's also a more formal definition of value types that I won't repeat here because there are great papers by Stepanov, for example, and there are great talks by Victor Kiura, for example. So if you haven't heard a lot about value types and about the basics of generic programming, then please check those out. In summary, a very simple value type that behaves like an int should be default constructible, it should be copyable, movable, assignable, and comparable. If it has all of these operations, we also call such a type a regular type. And all simple value types are regular. Ints, of course, but also more complicated STL types, strings and vectors, for example. And it is advised that if you write a value type, to make it regular. There's even a C++ core guideline that says so. And we do this so value types always behave the same. They behave in predictable and easy to use ways. So we do this for simplicity. We do this for consistency. We implement regular types. So how do we write a regular type in C++? At first, I will talk about semi-regular types that are not comparable. It turns out that this is super easy in modern C++. It just works by default thanks to compiler-generated constructors. We don't have to do anything in a lot of cases. So here, I've written a very simple value type contact that contains a lot of standard types, strings, an optional vector, and even a variant. And there is a concept, semi-regular, that I can use to statically assert that this is indeed a semi-regular type. And I didn't implement any constructor or destructor because the default automatically generated special member functions all do the right thing. This is also called the rule of 0. There is there's a blog post by Funatan about it, Jonathan Mueller, my colleague here at ThinkCell. So check that out. And that also works, of course, if our type contact would have another user-defined type. So the automatically generated special member functions are always correct as long as all our member types are themselves regular types and are copyable, default constructible, etc. Okay, so for very simple value types, that's super easy, nothing to do. Now let's look at the second kind of type I mentioned, containers. So containers should also behave like value types, but containers are special because they usually manage memory. And if you manage memory, then you have to implement those special member functions yourself. You have to make sure that memory is created, it is destructed, it is copied. And here we have the rule of 5 or 6 if you count the default constructor. And again, there's the same block entry on Funatan's blog. Here for containers, the rule of 5 or 6 means we have to implement all of those special member functions ourselves, as I've just said, to initialize, copy, and move and destroy the memory we have internally allocated. Then we have the third case. And the result, if that wasn't clear, the result is also a regular type. right? That's the beauty of it. Then we have the third case, resource wrappers. So these are C++ types that we use to wrap resources, a file or a database connection. Typically, these types are move only. You have an open file, you cannot copy that open file. Then you have the same file open twice or something. That doesn't make any sense. That file is opened once and it has to be closed once. So here we have C++ wrapper around the std file pointer. And it's not quite correct the way it is written now, although it would compile, unfortunately. So it's default constructible. That's fine. The file pointer will be null. It has a constructor to open the file, probably from that car pointer. But this type will automatically generate a copy constructor and copy assignment, which will just copy the file pointer. And that's wrong, of course. That's a resource that we have to manage. So a better implementation would look like this. So we implement a move constructor, and the move constructor moves the file pointer from the move from file into our file object and exchanges it with the null pointer in the other file. And here we've used this null pointer as our moved from state. That means when our struct file is empty, it has been moved from the container null pointer again, and we don't close the file in the destructor. So this is all still pretty basic C++ 11. Again, the same holds, of course, for the move assignment. You can simply implement that with the swap. So what I like to do, again, to make my programming as declarative as I can and to write down my intentions as clearly as possible, I like to have a little helper, which is called just non-copyable. And non-copyable I use as a base class. And non-copyable here, by declaring the move assignment and the move construction, implicitly deletes the copy construction and the copy assignment. So when I derive from non-copyable, I both declare that this type should not be copyable. It should be move only. And if I accidentally do something wrong or create code that tries to copy that file, then this will throw a compiler error because non-copyable is indeed not copyable. So I'm coming to my first very small C++23 feature, because move-only types, although they are very practical and happen surprisingly often, they had a very important problem. You couldn't really capture them in a std function object. But in C++23, there's now the move-only function object. And this was the problem. So you had a little lambda, and into that lambda, you moved your file, your move-only type. And now you have to assign, or maybe you have to assign that lambda to a std function object for some reason. And this would not compile, because std function was always copyable. So it would compile the copy constructor of that lambda, and that copy constructor of the lambda would try to copy the file, and that would fail. And now in C++23, we have the corresponding move-only function object, and this will indeed compile, and the function object is move-only, of course. So my last case was semantic singletons. So objects that you only have once, or that are maybe some of them you have only once, some of them are simply not movable or copyable. Mutexes, for example, are neither movable nor copyable. But you might also have a global resource, a cache of something that exists exactly once. And here again, I like to declare a little non-movable helper that I can derive from, that here deletes the copy construction and copy assignment, and consequently also makes the type not movable. So this is also a usable base class. So these are the four very common cases of life cycles of objects that we have to implement. So for simple values, we use the rule of zero. We don't do anything. For containers, we have to implement everything. The result should be at least a semi-regular type. Then we have move-only resource wrappers, and we have singleton objects. And we can use those little helpers to make their implementation easier. And now here we already run into a little problem in C++. It would be super nice if we could check at compile time that we did this correctly or the way we intended to. And we can't, unfortunately. I showed you the concept that a type is semi-regular, but that doesn't quite checks that you, well, I'll come to that in a minute. What does it not check? The problem is this. So here I have a type address, and that address implements a copy constructor. And now that copy construction will disable the automatic generation of the move constructor. So I have a type that is, in fact, never moved. It will always be copied. But I can assert that it's semi-regular, and I can assert that it's even no-throw move constructible, because the move operation will always fall back to the copy operation, because we implemented them with backwards compatibility when we introduced the move. So that's very unfortunate, but that's unfortunately a very rare problem. I mean, yes, we have to. I wish it was better, but if you step through your types occasionally and debug them or test them, then you can find out if you did this wrong. Okay, so these were pretty much basics of defining classes and their life cycle, etc. So now I will go into the missing operation for defining regular types, which is comparison. Then we'll talk a bit more about compile time evaluation, compile time allocations, how to make types formatable, and about deducing this, which is also a new C++ feature. So for value types, I've shown you how to make value types semi-regular. That was very easy. You didn't have to do anything. How to make them regular types, how to implement comparison. And that is very easy as well, because we can also use the automatically generated spaceship operator for that. By default, this will also do a member-wise comparison on all your members. So here, this works for contact because it works for all members of contact, including address, because for address, we implemented, again, the default spaceship operator. Now we have a regular type. So this is all great if your spaceship if the default spaceship operator does the right thing. Then let it be auto-generated. In general, defining equality can be surprisingly complicated, or defining an order over your types. Value types could, although I haven't shown you an example yet, value types can contain references or pointers to something or handles. So you can have a value type that contains an open file, for example. But in order to be a true value type, you have to compare this by value. So you have to compare the file contents, technically, if you do a value type comparison on that value. The good thing is that, well, you only have to make your types really regular if you really need the comparison and you know how to implement the comparison correctly for your use case. You can avoid it if you don't need comparisons at all. Because I have a little example that I can admit, I think happened at least once to me in practice, that it is pretty easy to implement comparison operators wrong. So here I have a slightly, how do you say, a slightly artificial example. So I have a simple type t that contains some data, an integer, but it also contains a pointer to another type t. Maybe imagine that's something like a tree or something. So I'm pointing to somebody else. And in order to be a true value type, if I have to point to something, I have to compare the contents of that pointer as well. So here, without thinking too much about it, I've written a little comparison operator that checks, well, if I compare two types t and they both have siblings, then I have to compare the siblings, hand waving. And otherwise, I just compare the data. And then I'm happy because my static assert, of course, says this is totally ordered. And then I try this out, and I don't want to show this too long. And then I try this out, and it turns out that my so simple looking comparison was in fact wrong. I've written an order that is inconsistent. See here, B is less than A is less than C is less than B again. That is obviously not a total order. Because I didn't follow the standard pattern of how to implement quality that I want to show at least once. So when I'm implementing comparison operation on a type, I try to think, I try to partition the space of all possible values of my types. And then we have to do a step-by-step comparison operations that consistently partition this entire space in smaller and smaller and smaller groups without, well, I hope by then it's clear that you didn't forget to make an important comparison that you should make. So here, when we're defining equality on that type T, the first thing we have to partition our types by is, do they have a sibling or do they not have a sibling? This is the part I forgot about. And so if they have a sibling, if both of them have a sibling pointer, then I can compare them by the contents of that sibling pointer. Otherwise, I compare them by their data. And if I then have compared them by their sibling member and they're still identical, then I have to compare them by the data themselves. So this is a partitioning that makes sure that I don't forget any important comparison I have to make. So in code, it looks a bit longer. It would look like this, for example. So I first compare two types T by checking, does one of them have a sibling or not? Then I compare them by that. Afterwards, I can assert, well, either both of them have a sibling now or both of them don't. And if they do, I compare them by the sibling pointer, or the value of that pointer. And last but not least, I compare them by their data. So as I've said, it's not trivial in some cases. Don't define it if you don't need it. If you do need it, do a proper partitioning of values so you end up with a total order. So back to the value types. What other nice property do we want that we get by default now? Now I can't really ask you, I think, as in a live conference. So just let you think about it for a second. What we want, because it's super practical, is compile time evaluation. And we also get that by default for a lot of the built-in types. So this type contact by default is constexpr. Constexpr constructible, constexpr copyable, comparable. And there are a lot of constexpr algorithms, of course, by now in the standard library. Std ranges fold left, for example, is new in C++23. So we can do out of the box, we can do a lot on our values at compile time. And the great thing about compile time evaluation that I like to mention at all times is that we get compile time checking of undefined behavior. So if by accident I wrote something like here, I'm dereferencing that age, although that's an optional that I've never initialized in the last line 17, then the compiler will notice. And he will tell me where exactly I made my mistake. So at runtime, this would have been undefined behavior, and we would have run into it, and then anything could have happened. At compile time, this will be checked by the compiler. So that is always a pretty cool feature, I think. So we want to make everything constexpr that we can make constexpr, just as a habit, including functions, if that's possible. It doesn't cost us anything. If they're not used at compile time, then there's no cost. And your future self will thank you if you ever need them at compile time and want to implement something non-trivial at compile time. So that means no undefined behavior. It means no lifetime issues. Everything you've done at compile time is safe and fast and UB-free. There are a couple of different types of constness in C++ by now. So I wanted to make a short little table to show you what's the difference between const init, and constexpr. So first, the good old keyword const. So if you declare a variable const, of course, it means it is constant. That means it is immutable. It also means it's thread safe, right? Because you can't change it. So you can read it from any thread at any time. Then we have const init. Const init, interestingly, does not mean that a variable is const, but it means that a variable is guaranteed to be initialized at compile time. That means there won't be a constructor. It will be initialized at compile time through a compile time constant. That means you don't have problems with the static initialization order. So since a const init variable is not const, you can, of course, declare const init const values. They are both constant and guaranteed compile time init, but that's not the same as having a const expr value, because a const expr value is also guaranteed to have a const compile time destructor. So this all is true for variables with static storage duration. Great. So most of what I've shown you so far was C++20. And I was under some pressure to include some newer features. And I found a good one. There are a couple more coming. So when we do compile time calculations, then we, of course, also need compile time asserts. We need static assert, right? But out of the box, you can write static asserts that don't have any error message, or they can have constant error message, of course. Well, that's really not so practical, because then this creates error messages that are not so useful. I would have liked to know maybe what T and T2 actually had as values. And now in C++, I think, C++23, I said, you can have error messages in static asserts that you've also calculated at compile times. So the idea was to use that with compile time std format, but I'm not sure if that is done yet. So I had to write my own poor man's compile time std format that takes my two strings and concatenates them, and this is all const expr. And I can now pass this to static assert as a dynamic compile time error message. And indeed, we get a much better error message that tells me that hello is not equal world. And the return value of my poor man's std format has to be any type message, any object that has a size member and it has a data member that returns a string. And then you're good to go. So definitely a good feature if you're doing a lot of compile time calculations. Now, speaking about const expr, there's another thing that was new in C++23. You can now use unique pointer in compile time, in const expr expressions. So again, we get 3 checks for undefined behavior. So here we can create our value of type T at compile time in line 10. That will create a default constructed unique pointer. That's perfectly fine. And we cannot access that pointer, of course, because it hasn't been initialized. It's null. Dereferencing the null pointer is UB, and the compiler will tell us so. Okay, but how do we use the unique pointer at compile time? How do we do memory allocations at compile time? So you try to do this, and this won't work either. The compiler will say that our default constructor for T is not a constant expression because it refers to a result of operator new. Okay, by itself, not very helpful if you don't know how compile time applications work. This will work. So we create a type T that will create a unique pointer at compile time, and then we access that pointer and access member I, and then this will indeed compile at compile time. So what's the difference between those two cases? The difference is that allocations, that compile time allocations have to be transient. That means inside a statement that is evaluated at compile time, you can make allocations as long as that allocation has been deallocated by the end of your compile time evaluation. So this is true here. By the time I've calculated n, I can deallocate t in my unique pointer and everything is fine. This is not a very useful example, probably. This is more useful in such contexts. So imagine you have some function or some data type that internally has to make allocations, and you want to use them in a const_expr context. And now this is fine, even if they create unique pointers, as long as that memory has been deallocated by the time you have evaluated your compile time statement. So these are called transient allocations. This is, of course, how we can use vectors and strings in const_expr functions, right? They also have to make allocations internally at some point. And again, because I've said we get those automatic checks for undefined behavior now at compile time, we can abuse this as a checker for memory management bugs. If there's any location where you still do manual new and delete operations, you can try declaring those contexts as const_expr and try to evaluate them at compile time and see if that indeed compiles. And then you've proven that you don't have a memory leak. It's probably better to remove the new and delete, but you can also have a compiler check. So the const_expr allocation was C++20 already. The unique pointer is C++23, and there will also be a placement new operator, which will probably come in C++26 to make const_expr ever more powerful and useful. Okay, what else have we got? We have our great regular type. It is const_expr. What else would we like to do? Well, would be cool if we could do this, right? If we could just print our type C to std out. And now this is also very easy to do because this is what std format is there for. There's also a new concept, formatable, that we can use to check if our type is formatable. And so let's go into some detail how we can make our type work with std format. Okay, let's remove that and let's go here. So what you have to do to make your types formatable is to specialize the formatter type. Here I specialize it, of course, with contact. So this is my template specialization for the formatter. And I say I'm outputting characters. And the formatter has two functions. The first one we'll not deal with now. The first one is the parse function. It has to be a const_expr function that is used to compile the format specifiers. So if in std format you want to specify how our contact would be formatted, you can do this here and you can parse that specifier here. And then the important one is format. So format gets the contact, of course, and the context. And the most important part of that context is context.out, which is an output iterator that we can just write to. And here we use the format API again to output all our members or some of our members to that output stream. That includes, by the way, the range formatting here because the emails is a vector, I think. Range formatting is also new in C++23, that you can just output ranges with std form. Okay, and here's the format too. Okay, the other function was the parse. Implementing the parsing is also relatively simple, so you get that parsing context. The parsing context contains an iterator to the format specifier. So let's say we want to have a very simple context specifier that is only a P, so we can write a P if we want our format to be very private. And if it's private, I think it won't mention my age. So we are just dereferencing the iterator. We are checking if that's P. We are storing that in our std formatter specialization. And we also have to check if we're done with parsing or if there are any unsupported format specifiers. And that's already a very simple implementation. And then we can use that in std format. And so if we want to be private, then I'm just printing my name. And otherwise, I'll tell you everything I know about myself. So here, the cool thing about stitch format, of course, was that the format specifiers are parsed at compile time. That's why the parse function has to be a const expr function. And so it can give you compile time errors if your format specifiers are wrong or don't match the variables you pass, unlike printf, right? Sometimes, though, this is a very strong limitation. Sometimes you just don't have those format specifiers at compile time, but you have to generate them dynamically. I also have an example for that. So here I want to implement that privacy feature at runtime by building a format string at runtime. And in C++26, there will be this std runtime format, which will allow you to pass a format specifier that has been created at runtime instead of at compile time. Okay, so that's formatting types. So there's more documentation about the format context, the parsing. There are built-in formatters for pair, for tuples, for ranges, thread IDs, stack trace entries. They're also new in C++23, I believe. So now we have pretty useful and well, pretty useful value type, right? It's a regular type, it's a formatable type, it can be evaluated at compile time. Of course, here the std print line function is also new in C++23 to make it easier to print stuff to, well, to std out in this case, without using the IO streams library. Cool. So that leaves one last feature that I also think is pretty great, and it does solve a very annoying, or part of a very annoying problem. So let's say we have our nice value type here, contact, and we want to access the emails. So here, this is just a public member variable. Maybe that's good enough for you, but very often we want to make that member variable private and hand out the emails by writing a public accessor function. Maybe just to make that member private, but you could also assert invariants in there, lock something. So there are many reasons why we sometimes do that inside a method. So the canonical way to do that in C++, I would say, is to return a const reference and to make that method then a const method, right? This is what we do in probably 90% of the cases. But this has an undesirable effect in some circumstances. Let's say we have a function make contact that returns a contact by value, of course, a temporary object. And now we, in some context, sometimes this can be a generic context, so it's not so obvious. You create that temporary contact, and now you call the get accessor on it. And there are only there's only one correct way to handle that. And this is to get that vector copied. So let me rephrase that. The get accessor always returns a const reference. And I can copy that into a new vector. That is correct, but unfortunate because I wouldn't have to do the copy. I can also write and compile the second line, autoconstref vec2 equals make context.get. This will compile, but it will create a dangling reference because my temporary contact will go out of scope. My reference won't be kept alive, but the compiler doesn't know that. And I've now written myself a pretty nice bug. And this is all very, very unfortunate. And it's easy to get this wrong, especially in generic contexts. This is especially unfortunate because if I would just access the member emails, then this would always be correct. So here in the comments, I've written that as like, well, simpler statements. If I get the emails member of a mutable reference context, then that will be a mutable vector of strings. If I get the emails of a cconstref, then this will be a constref vector. And if I get the emails member on a temporary, and that's the interesting case here, then this will be an R value reference. And I would have moved the R value reference into my left-hand side. This is what I would have wanted. With the member function, I destroy this very nice property of value types. And now the reason why this happens, of course, is that I've written a const member function. And this simple const member function can be called on all types of L values and R values. So this compiles when I call it on a temporary R value object, but it will give me an invalid vector constref that will be dangling in a second. So you think, okay, well, the const function, that is actually old school C++, we have introduced ref qualifiers. So for the ref qualifier, I could now say, hey, this member function get should be a const ref member function. But again, this doesn't help us because const ref functions also bind to all values. So I can call this on mutable references, and I can call this on R value references for the same reasons of backwards compatibility that we've discussed before. Const ref binds to anything, to temporaries and non-temporaries alike. The only solution, since we had const ref qualifiers, was to overload all versions of them. And then the right thing would have happened. If I call this on a temporary object, the getRefRef overload would have been called. That would return R value reference to the vector that I could have moved out of. Great, but this is no way to program, right? Who does that? So now the explicit object parameter, also called deducing this, comes to the rescue, and that allows us to write member accessors that do the right thing always for L value and R value references alike. Because here the template argument, this self, will resolve to the this pointer. So it will then deduce, depending on what type the this pointer was, R value or L value reference, it will create the correct reference for the emails vector. If I write my accessor like this, the original problem goes away. I can write it like this. I can create an autoconst vec out of this, and this will create the right move. This is great, definitely better than before. Unfortunately, we still have this lifetime extension feature that we should probably remove. This still compiles and this still dangled, so it's still easy to get this wrong because it does the right thing in some circumstances, definitely does the wrong thing in that circumstance. So that's still wrong. Don't write it. What we would like is probably to have some way of declaring that the left-hand side here should be a reference if it's safe to get a reference, and otherwise make this a value if I have to move out of a temporary. This is something we have written for ourselves in our open source library. It's a macro, unfortunately, but this can be useful in generic contexts because it does exactly that. If you have implemented the correct get accessor, of course. So this is now safe and does the right thing in all circumstances. The only other solution, if you don't want to do this, and you don't want to use this macro, is actually to write accessors that are deleted for R values. That's also safe. It also solves the problem. Okay, that's essentially my talk. So in summary, follow the simplest lifecycle best practices for your types. Make value types regular. Make resource wrappers move only. Make everything const expr or const init if you can. Use std formatter, and write your accessors using deducing this. Thank you very much. I think I might have been a bit fast because I didn't see your faces. So I apologize. You can later watch it on YouTube in slow motion.